All right, let's dive in. Today, we are pulling back the curtain on the tech that powers tools like ChatGPT. I'm talking about large language models. We're going to find out how they actually work from the ground up. You know, it really does feel like magic, doesn't it? That a machine can just write a poem or debug some code or answer some really complex question. But what if I told you that at its very core, it all comes down to one single, surprisingly simple task? That's the mystery we're going to unravel today. So let's forget all this science fiction stuff about conscious AI for a minute. The absolute best way to start thinking about a large language model or an LLM is to just picture the most powerful, souped-up autocomplete you have ever seen. Seriously, its entire job, its whole purpose is to look at a bunch of words and then make a really, really good guess about what single word should come next. And that one simple goal, just predicting the next word, that is the bedrock for everything else that follows. To really get how these things work, we have to start right here with this one core function. This really gets to the heart of it. So when a model sees a phrase like, the sky is, it's not thinking like you and I do. It's not picturing a sky. What it's actually doing is running this massive mathematical calculation, and it's assigning a probability score to thousands and thousands of possible next words. And based on all the text it's ever read, a word like blue is going to get a super high score, while a word like bug gets a ridiculously low one. It's all just statistics. Okay, so how do we get a model that can calculate all those probabilities? Well, you have to build its brain completely from scratch. This first part is called pre-training. And this is where we create this incredibly knowledgeable but totally unrefined raw intelligence. To build this brain, you need a staggering number of what are essentially tunable knobs that the model can adjust as it learns. They're called parameters. A model like GPT-3 has 175 billion of them. Each one is just a tiny value that gets tweaked over and over again, making connections between concepts stronger or weaker to get better at its predictions. And what do you feed a brain with 175 billion knobs? An unbelievable amount of text. GPT-3 was trained on 45 terabytes of data. I mean, that is a huge chunk of the entire internet plus countless books and articles. It's basically a massive library of all of human language and knowledge. And just to put that number into perspective, if you were to sit down and read nonstop 24/7, it would take you over 2.5 millennia to get through the same amount of text. That is just the sheer scale of the experience we're talking about here. This quote just sums it up perfectly. After all that pre-training, the model is incredibly knowledgeable. It's learned the patterns of physics, of history, even humor, all just from predicting the next word. But, and this is a big but, it has no idea how to be helpful or safe or how to follow a simple instruction. It's just this raw, powerful pattern-matching engine. So, how do you turn that raw, book-smart intelligence into something like a useful assistant? Well, that's where the next phase comes in. This is where we, as the trainers, step into the picture to kind of polish that raw brain and align it with what we humans actually want. The key technique here has a fancy name, reinforcement learning from human feedback, or just RLHF for short. This is the absolute secret sauce that turns a model from just a text predictor into a real conversational chatbot. It's how we teach it the difference between a good answer and a bad one, not based on some math formula, but on what we humans actually prefer. This chef analogy makes it super clear. So imagine our raw LLM is this brilliant but kind of chaotic chef, right? A customer orders a dish. The AI chef whips up 4 different versions of it. Then a real human taster comes in and ranks them from best to worst. That ranking is the critical feedback. Now, get this. We train a second, totally separate AI, a reward model, and its only job is to learn how to predict the human's rankings. And finally, we use that reward model as an automated judge to fine-tune our original chef. We reward it for making dishes that the reward model thinks a human would love. You do that millions of times, and pretty soon the chef learns to cook exactly what people want. Okay, so we've gone through this whole structured training process, but this is where things get really, really fascinating. When we push these massive models to their absolute limits, all these strange, unexpected behaviors start to pop up. Things that surprise even the researchers who build them. It's kind of like discovering a ghost in the machine. One of the most amazing things they found is called grokking. So imagine a model is training on a math problem. For a long, long time, its performance is just terrible. It's just trying to memorize answers. But then,
All of a sudden, its accuracy just shoots up to nearly 100%. It hasn't just memorized more stuff, it's had this aha moment. It has actually discovered the underlying rule or the algorithm. It has truly grokked the concept. Here's another really strange one that completely breaks the old rules. So normally, you make a model bigger, it gets better, but only up to a point. Then it starts to get worse because it's just memorizing the data. But with these LLMs, something called double descent happens. The performance gets better, then it gets worse as it starts to memorize. But then, and this is the wild part, as you keep making it even bigger, it surprisingly starts getting better again, often way better than it ever was before. It's almost like it's being forced to find a smarter way to understand everything. And this leads us to this idea of emergent abilities. These are complex skills, things like solving logic puzzles, that just don't exist in smaller models. But once a model gets big enough and sees enough data, these skills just emerge. Now, there's a huge debate about whether these skills are really appearing out of nowhere, or if maybe our tests just weren't good enough to see them before. And the weirdness just keeps going. Researchers found these funny quirks, like the model focusing a huge amount of its attention on the very first word or punctuation mark in a prompt, almost like it's an anchor. And this has led to a new theory about those emergent abilities. Maybe they aren't some magical leap in skill. Maybe it's just an illusion. The idea is that the model is improving steadily the whole time, and it only looks like a sudden jump when its performance finally crosses the pass-fail line on our tests. So, with all these incredibly complex behaviors, what are these models actually building inside those billions of parameters? And that question leads to a really profound, almost philosophical theory about what intelligence even is. It's called the Platonic representation hypothesis. The theory basically suggests that as all these different AIs built by Google, OpenAI, Meta, whoever, as they all get smarter, their internal maps of the world start to look more and more alike. It's as if they are all independently discovering the same fundamental, maybe even perfect map of how concepts relate to each other. And this right here, this is the ultimate takeaway. That simple goal of predict the next word, when you do it at a massive scale, it forces the model to do something absolutely incredible. It forces it to build an internal model of our world, of physics and logic and human psychology, all just to make better predictions. We're not just building sophisticated parrots. The process itself seems to be uncovering the very structure of knowledge. And that leaves us with this final, really tantalizing question. If all these different digital brains, all starting from different places, are all ending up with the same internal map, what are they actually discovering about reality, about language, and maybe even about us? What does that map actually look like?